Okay, so I've suggested a few times on Piazza and things that you guys really help yourself out by just opening up a Google Doc and summarizing what you know, especially the Julia commands. You'll find out there's like 6 things we use over and over, okay? What I'm going to try to do is incentivize it just a tiny bit. The details are on Piazza under the lecture tab. This is not a required assignment. It doesn't count as part of the grade, but inevitably, and this is one of the things I hate, is, you know, I got to draw a line. And Monty and Tribby and I will talk about it and try to do it as fair as possible. And then somebody is like right below, like 0.1 points or something, and the next person, they're just, and so I just want a reason to push you over, okay? That's all it's going to be. If you're just below, I'll push you over if I look and I see that you've done a good job and you've worked hard to acquire the material. That's the only place it'll be used. You land up with a really big fat A or a really big fat B right in the middle, it doesn't change anything. So it's only if you're on the edge. And Michigan makes me turn in a letter grade, which is then converted into a number, which is then averaged over all your courses, and then becomes a decimal number, okay? But I am not allowed to turn in a 3.64 as your grade. I have to assign a letter on it, which is kind of stupid when you think about how GPAs are computed. But so that's my offer, and that's my method of incentivizing you helping yourself. Okay, back to material. We've been working on essentially existence and uniqueness of systems of linear equations. And one of the equations we looked at was a matrix A, which is potentially rectangular, n by m, times a vector of coefficients we called alpha. It has to have the same number of coefficients as A has columns, so it's m by 1, and that equals 0. And here I'm emphasizing it's the 0 in Rn, because A has n rows. That equation is completely equivalent. They have exactly the same solution if you multiply on A transpose on both sides. You get A transpose A equals 0. We went and proved that. That was the basis of our pro tip. It was all well and done. So A transpose A is m by m, it's square. Alpha is still m by 1, and this is now the 0 in Rm, the number of columns of A. So you can always help yourself out if you just remember 0, but it's not always the same 0. It's the 0 in the real numbers, it's the 0 in Rn, 0 in M1. Sometimes writing that out helps you think about, do you have your dimensions correct and stuff. And so there exists a non-trivial solution to A alpha equals 0 if and only if the columns of A are linearly dependent. And that's if and only if there exists a non-trivial solution to A transpose A alpha equals 0. The nice thing about A transpose A is that it's square, and we know about uniqueness of solutions of square systems of equations. You look at the determinant of the matrix, okay? So the columns of A transpose A are linearly independent if and only if determinant A transpose A equals 0. And that's the 0 as a real number. It's a 1 by 1, except in Julia, it's not a 1 by 1. It's a scalar, okay? But it's a 1 by 1, just keeping the dimensions straight. So that's a good summary of rectangular to square and equivalences of concepts in terms of linear independence. Now, these following remarks are paraphrased from questions posed in office hours. And it wasn't posed exactly like this, but what does uniqueness of solutions mean for a system of linear equations? And bottom line, it means if 2 different people compute a solution, they have to agree. That's what uniqueness means. So I'll make the two people me versus you. Okay, so I compute a solution, you compute a solution, and we both do it correctly, then they have to agree. So here's an example. Here's an A. It has one row and two columns. One row, two columns. Here's our X. It has two components, and it's equal to a B, which is just a scalar. So that's the same as the equation x1 plus 2x2 equals 3. You compute a solution, x1 equals 1, x2 equals 1. Sure enough, that works. It's a solution. Me, I go with x1 equals 3 and x2 equals 0. Hey, I did it right too, okay? We disagree. How is that possible? It's because the solution is not unique, and that means that, yes, I can write 2 as a linear combination of 1. It's 2 times 1. The columns of A are not linearly independent, so the solution is not unique. This is a trivial, really down simple, but just trying to make the concepts concrete. So why is linear independence important? Because it's exactly tied to the question of uniqueness of solutions of AX equals B. Okay, a little reminder, I did my mail-in ballot, so you should vote. Now, what does linear combination mean for a system of linear equations? Okay, well, my answer here is let's see. Let's do another kind of simple equation. The matrix has 2 rows and 1 column, so it only has one unknown, x1, and it's equal to then 2 things on the other side, b1, b2. If I make a choice for b, that's say 1 and 1, then these are the 2 equations I have. I end up with x1 is 1 and 2x1 is 1. And you recognize that as being an inconsistent system of linear equations. No solution. However, if I choose B1 and B2 to be proportional to this column, okay, so then B is a linear combination of the columns of A. I made it simple for me so I couldn't get it wrong. I've only got 1 column, okay, but if there could be 2 or 200, then the equations are consistent, okay? And so consistent equations means we have a solution, and the necessary and sufficient condition is that B is a linear combination of the columns of A, and that works for AX equals B when it's rectangular, square, we just don't care. How's that? Does that lock the concepts in a little better, or am I just wasting your time? I'm wasting your time. I'm wasting my time. I'm wasting Tribby's time, Caitlin's time, everybody's time. Okay, so, and the nice thing is once you have these concepts, they scale to systems of hundreds of variables instead of 1 or 2, okay, and then we have all of these matrix factorization methods to actually compute stuff very conveniently. Okay, so here's the kind of the final problem in this chapter. It's been more difficult than the other chapters, I think. There's more concepts in it. Linear independence was hard. Counting number of linear independent vectors was hard. Linear combinations was harder than just looking at AX equals B and saying, oh, it's triangular. I do either back substitution, forward substitution. There's more concepts here. So here's the final one. How do we actually solve for the alpha that gives me a linear combination of the columns of A that's equal to 0? How do I actually find a solution? Okay, so if the columns are linearly dependent, I know there is a solution, but do I have to grind through the terrible equations that will typically be here? Because there's no special structure in A. It's not triangular in general, so it's really painful. Okay, so the situation we're looking at is determinant of A transpose A is 0. That means the columns of A transpose A are linearly dependent, and that means the columns of A are linearly dependent. So how do we solve for that value? And we have you do this in the Julia Homework 5, which is next week, okay? And we tell you to read the book. We don't tell you how to do it. You just have to do it. So I'm being super kind, and I'm going through this. So we'll do it with an example. I'll take A is 1, 1, 3, 0, 0, 1, 0, 1, 1, 2, 3, 4. Okay, are the columns of A linearly independent? V1, V2, V3. On this simple example, we can do it by inspection, okay? We just notice that V1 plus V2 equals, whoops, I don't want to, I usually put subscripts. Sorry, I'm putting superscripts, okay? I'll fix that. Oh. Get my black guy back. There we go. That was a 4. And then we notice that V1 plus V2 plus V3, excuse me, V1 plus V2 equals V3. I got all messed up with my superscripts and subscripts. Okay, so V3 is a linear combination of V1 and V2, and hence they're not linearly, excuse me.
How does the bottom
work? Oh, that one doesn't work. So what is it? I computed this one. Oh, it's a little more complicated. Okay. Let's see, I need a 4 here and a 4 here and a -2. Okay, if I've done my numbers right and I don't remember the combination, we'll check it at the end, okay? So we'll check this at the end. So point well taken, okay? Check at end. Okay, so maybe it's false, right? So this is the typical problem. So we know AX equals 0 if and only if A transpose AX equals 0. Now, hopefully I did these computations correctly. We're going to compute the LU factorization of A transpose A. Okay, so let's just note P times A transpose AX equals 0 if and only if A transpose AX equals 0. And that's because the determinant of P is always plus or minus 1. So it's invertible. Okay, so I take P inverse here, and P inverse here. P inverse here is 0, so it's gone. And then I have A transpose A, and then if I have this, I multiply by the P here and the P here, and I recover this equation. So that's always true. Okay. And then P times A transpose AX is equal to 0 if and only if then L times ux equals 0. But L is unitriangular. Remember, it has ones on its diagonal. So the determinant of L is always equal to 1, so it's invertible. So we get down to the end is that A transpose AX equals 0 if and only if UX equals 0. Okay, so this is a really good thing because this is triangular. And these type of equations we can solve much, much easier than, see, I couldn't even solve this one in real time. You guys figure out the answer while I've been doing the other calculations? Somebody has already put it into Julia on the online students, and they have the answer. Okay, so if I copied everything correctly, in our case, we end up with U equals this, 24, 6, 30, 0, 1, 1, 0, 0, 0. Okay, so here's the diagonal of U. Okay, so it should be the case. So determinant of U equals 0 if and only if determinant A transpose A equals 0 if and only if columns of A are linearly dependent. Okay, so how do we solve UX equals 0? That's the question. Okay, so we want UX equals 0. What is X? Okay, well, I'm going to write it down again. 24, 0, 0, 6, 1, 0, 31, 0. Just so I can put my X1, my X2, my X3, and it's all 0, 0, 0. Let me do this. Okay, those are all zeros, even though they look like sixes. Okay, what value of X3 can I plug in here and have this equation be satisfied? Anybody got one? Any value. Yeah. So how about X3 equals 1? Pretty good choice? Okay, so this is how it goes. I'll write it down a little bit more, but X3 is free. This equation says X2 plus X3 equals 0. So what is X2 then? Minus 1 if I chose X2 as 1. And then this equation says that 24x1 is plus 6 times x2 plus 30 times x3 equals 0. So it's a triangular system, and it's trivial to start at the bottom and work your way up, okay? So ux equals 0 is equivalent to, and this will help some of you to see what's going on. X2 plus x3 equals 0, and then 0 times x3 equals 0. Okay, so x3 is arbitrary. So we take, say, x3 equals 1. You're free to choose x3 equals 17 or just to keep x3 a variable and then plug in anything you want, but I just plugged in a number. So then conclusion, x2 equals minus x3 equals minus 1. And then conclusion, 24x1 equals minus 6x2 minus 30x3. And so that's minus 6 times minus 1 minus 30 times 1. Minus 6 minus 1 is plus 6 minus 30. This is minus 24. And so 20, this is how I have my numbers arranged, so I hopefully have A correct, but then we get x1 is equal to 1. Okay, so then x equals 1 minus 1, 1. Okay, so let's go back and just check that. It's not looking very promising, but so I must have messed up my numbers because the theory says it has to work. Even the first thing, that's 2. So obviously I made a mistake on what my A matrix was, okay? Oh, let's see, that was -1, so that's 0, okay? And then 1 minus, those two things cancel though, then I get 2 here, right? So there's still a problem someplace. So he spotted it right away. Grizzle's numbers are wrong, but the method is correct, okay? I've learned not to fake it, just own up that you're a schmuck, and then you guys can figure it out what's going on, okay? But the method is correct. Sorry about that. Okay, I don't get a smiley face today. Yeah, so.
The first number if the last number on the first column is 3, will be good.
Yeah. So it's not 1, 2, 3, 4 though.
And then the LU will also be right.
Yeah. Tribby's already so smart that she's figured out how to re-engineer my example, reverse engineer it, then forward engineer the answer. But I think I reminded you guys that when you're up here, your IQ drops by at least 20 points, okay? So if anybody want to swap places with me, come on up. We'll give it a shot. Okay, so that's the end of chapter 7. So we're moving on to chapter 8. Okay. It's on norms and least squared error solutions to linear equations. Okay, so let me just punch in the objectives and make some comments about those. So these are all in the book, image, file. Chapter 8 objectives. Yay. Come on, where'd you go? Try it again. Chapter 8 objectives, open. Oh, I can't get my numbers right and my objectives won't paste in. Where'd you go? No. Okay. One more time and then I'll just write them in. There you are. Open. Okay. Life is hard. I'll do a shorter summary then. So here's sort of a meta thing that's not written in the book, but it sort of is there. In engineering, as in life, get out of here. You're not helping me today. The most interesting problems do not have exact answers. Okay. So we're going to be looking at equations that just don't have solutions. AX equals B, and B is not in the column span of A. B is not a linear combination of the columns of A. Okay? So we're going to pose a notion of error, and then we're going to try to minimize that error. That's what the word least means. Okay? And so you're going to learn something that's super cool. Linear regression. And I think about it as one of the superpowers of linear algebra. Okay, this sets you up for solving almost any type of linear algebra question that comes your way. If it has AX equals B and it has a solution, you guys know how to compute it. But now what do you do in the realistic case of when the equations are not consistent, not perfectly consistent, and when you make measurements, they're never perfect, so your equations come out to be slightly or less slightly, meaning more inconsistent than you would like them to be. So to attack this, we first have to look at what is the notion of length of a vector. So we call that norm, and it's a notion of length. And for us, we're really going to use it by looking at an error between a times x minus b. That's going to be a vector. When it has a solution, that is the zero vector. It's going to have really short length, zero length, okay? That's a perfect solution. When it doesn't, how small can we crunch down that error? What is the minimum? Does a minimum exist? Is it unique? Are there 7 minima? Whatever. What's the situation? So the first thing we need is a definition of a norm. Okay, so for v equals v1, v2, dot, 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 vn, an element of the vector space Rn, we're going to use the symbol double bar, and it's by definition equal to. We're going to first take all of the components, square them, and then we take their square root. Okay? So it's sum of the squares of the components, square root. That's called the norm. Okay, that's simple enough. We'll do some calculations. Let's just note we can also write this. Okay, so remember when we did y transpose times y and we got y1 squared, y2 squared, etc.? So the same thing happens here. The norm of v is v transpose v square root. Right, so this is n by 1. The transpose will be 1 by n times an n by 1 is a 1 by 1. It's just the sum of the squares. So this and this are the same. And then, you know, if you like your sum symbol, so you know how to do it in a for loop, if you were going to do it that way, you could just add up these things and take the square root. So they're all the same. And then just as a little remark, if we square the norm, we get rid of the square root, okay? It's this very tiny little remark, but it's sometimes really useful. So this becomes v1 squared plus v2 squared plus dot, 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 vn squared, but that's v transpose times v. So just a little remark. When we get into the theory, a little bit about the theory about what are these least squared solutions, etc. It's convenient to get rid of the square root and you work instead of with the norm, you work with the norm squared. So it just gets rid of the square root. Okay, so let's just calculate a few norms. I don't think you guys will struggle with that, but okay, so vectors are just numbers organized. So I'll use some complicated numbers. There's my vector. What is its norm? Well, I'll first compute the square of the norm, and then I'll take the square root. Okay? So I'll do square root of 3 squared, minus 1 squared, square root of 5 squared, So I get 3 plus 1 is 4, plus 5 is 9. I'll let you catch up. So then the norm is the square root of 9, which is 3. Yay. Do one more. Minus 2, 7, 6, 4. Norm W squared would be minus 2 squared plus 7 squared, 6 squared. So it's 4 plus 49 plus 36 plus 16. And I think that's 105. So the norm of W is the square root of 105. And that's like 10 point something, okay? So just get your calculator out. So that's how you calculate the length of a vector. Some simple properties. The norm of a vector equals 0 if and only if the vector equals 0. Okay, so this is the 0 in the real numbers, and this is the 0 in Rn. That's obvious because you sum up all of the squares of the components, and so the only way that you get this to be 0 is if all of the components are 0, so then you get the 0 vector. So that part is obvious. The next part is a little bit less obvious, but for any real number alpha, so scalar alpha, and vector v in Rn, the norm of alpha times v is absolute value of alpha times the norm of v. Ooh. Okay, so if you multiply the vector by minus 3, you multiply the norm by 2. Okay. So let's just do v in R2. And so we'll do the norm of alpha times v1, v2, and I'll compute the norm squared, just as I've done before, and then we'll take a square root. Okay, so that's the norm of the vector alpha times v1 and alpha times v2 squared. So that's alpha times v1 squared plus alpha times v2 squared. But I can factor out an alpha squared times all of those and leave myself with the v1 squared plus the v2 squared. And so now I do the square root, and we know that the square root of a product is the product of the square roots, okay? So we do norm alpha v1, v2 is then equal to square root of alpha squared times the square root v1 squared plus v2 squared But the key thing is the square root of alpha squared is always a positive number. Okay, so that's where the absolute value comes from. Alpha, even if it's -3, let's say, turns into -3 squared, which is 9, and you take its square root, you get +3, so it's the absolute value. Okay. Cool, we're gonna have just enough time. There's one more property. For any pair of vectors, V in Rn and W in Rn, the norm of the sum of the vectors is upper bounded by the sum of the norms of the vectors. Okay. This has a name. It's called the triangle inequality. So do you guys remember from high school, if you have a triangle and you add up any two sides, that's greater than or equal to the length of the third side? It doesn't matter which of the two you choose. Is it the same thing here? Okay, so I'm going to take V1 equals 1, 1, and W equals 2, 3, so that V plus W is 3, 4. Okay, so let's see if I can mark off 1, 2, 3, 4. 1, 2, 3. Oh, I'm doing them. I can't even mark off things correctly today. Grizzle, what's wrong with you? You haven't had COVID. There's no, okay. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so here's the vector V plus W is at 3 and 4. So that's V plus W. Let's put V in there. V is 1, 1, 1. So V goes here. That's V. And then if you do the head to tail addition, this is W. So there is a triangle there, is the point. And the length of this one, if you do a good drawing, is less than or equal to the length of this vector and the length of this vector. So that's the triangle. That's why it's called the triangle inequality. Okay. So, least squared error. Why should we care? Ooh, that's bold enough. Okay, we're going to revisit an example that nobody liked when I did it, so we'll see if we like it the second time. fitting a line to data. Now the good thing, if you guys remember this example, that was the same week we posted the Greek alphabet rap. Remember that? Several of you were playing it like crazy, okay? So this is what was going on. So here's my data. So I'm going to do another one of these quality plots that only I know how to do poorly. Okay, so here's my data. And this time I need to go out to 7. 1, 2, 3, 6, 7, 5, 3, 1, and I'm using 2, 1, 2, 7, 5, 7, 7, 5, 3, 1. Okay. So my first data point is at 1, 2. 1, 2. Here's one data point. My next data point is at 3, 4. So 3 on the x. Whoops, even I can't do that right. 3, 4. There's my another data point. And my last data point is at 7, 5. So 7, it looks like it's here. Okay, so this one is 1, 2. This one is 3, 4. And this one is 7, 5. Okay, can you put a line exactly through those 3 points? The answer is no, okay? Imagine there's 15 of those things and they're all kind of, blobbed out in through here. You could still try to find the line that fits the data best. So that's the problem. So we seek a linear model. A linear model that explains the data. Okay. Now, we tend to write those things as y equals mx plus b. So I have 3 data points. yi is m and xi plus b. So the data points are in the form xi, yi. So I have 3 data points. My unknowns are the y-intercept and the slope. Okay, so for some reason, I'm going to put the slope on top and the y-intercept on the bottom. But who cares, okay? Those are the unknowns. So I'm going to take and write this out once again in the form so y1 was 2, x was 1, then of course what's multiplying the y-intercept is 1. y2 is 4, x was 3, and my y-intercept is 1, and y3 was 7, my x was 7, my y-intercept was, it wasn't 7 and 1, it was 7, 5. This was 5. Okay. Okay, so I'll call this y. This will be a regressor, okay? And this is my vector of unknowns. I'll call that alpha. So I have the equation y equals phi times alpha. Okay, so we'll pick it up here, but question, is 2, 4, 5 a linear combination of 1, 3, 7, and 1, 1, 1? And you can check it's not, so there is no solution to the equation. What it means that there's no solution to the equation is that you can't fit a line perfectly through it, so it's not consistent. But now we're going to try to find the line that goes through here and minimizes the data. So you could do that one, you could do that one, you could do that one, you could do something in between. We're going to find the formula that gives us the m and the b that minimizes the sum of the squares of the error. And that'll be our superpower. So Friday, we'll pick it up here with my graph drawn a little bit better, and we'll go on. So thank you.